Hello everyone, today we will continue to learn about the determination of the three elements of a function. Previously, we learned about the definition and three elements of a function. Can you answer the following question through the definition and three elements of a function? Question 1. The set A, B and their corresponding relationship f are shown in the figure. Does f form a function of set A to set B from A to B? If so, what are the corresponding rules for locality and value range? Students may have doubts when they see this question. Is it a function from set A to set B? It seems to be different from the linear, quadratic, and inverse proportional functions we learned in junior high school. Because the linear, quadratic, and inverse proportional functions we learned in junior high school all have analytical expressions for functions. And from this question, it seems that we cannot see the analytical expression. So, based on the definition of functions we learned in the previous class, can we use our high school knowledge to interpret whether the transition from set A to set B is a function? Based on the function definitions we learned earlier, we know that firstly, set A and set B must satisfy the condition of being two non-empty sets of numbers. Our set A is 1, 2, 3, 4, and 5, and set B is also 1, 2, 3, 4, and 5, obviously satisfying the condition that set A and set B are sets of non-public numbers. So in the function definition, we also need to require that any element in set A has a unique element corresponding to it in set B. Let's look at the correspondence between these two sets. In set A, 1 corresponds to 2, 2 corresponds to 2, 3 corresponds to 3, 4 corresponds to 5, and 5 corresponds to 4. So any element in set A, 1, 2, 3, 4, 5, can find a unique element corresponding to it in set B. So according to our high school definition, we know that a functional relationship is formed from set A to set B. Since it constitutes a functional relationship, what are the locality, value range, and corresponding rules of this function? According to our high school definition, the definition of a function should be composed of any element in set A. So the definition of our function should be a set consisting of 5 numbers, 1, 2, 3, 4, and 5. And the value range should be the numerical value obtained by any element in set A according to the corresponding rule. So the value range of this function should be composed of 4 numbers, 2, 3, 4, and 5. So, since it constitutes a function, we have also found the locality and value range of the function. What is the corresponding rule for this function? Do we have an analytical expression for a function that can represent the correspondence from A to B? Through the correspondence we just mentioned, we found that there is no certain pattern between the independent variable and the function value, which can be expressed using an expression. So what is the corresponding rule for functions at this time? We went from A to B. As we mentioned earlier, it doesn't seem to have a clear correspondence with the linear, quadratic, and inverse functions we learned in junior high school. For the correspondence relationship of this function, we can say that 1 corresponds to 2, 2 corresponds to 2, 3 corresponds to 3, 4 corresponds to 5, and 5 corresponds to 4. From question 1, we can see that for the range of values of the function, the set it corresponds to should be a subset of set B, not necessarily set B, and the correspondence rule of functions may not always be related to functions. It can be expressed using the analytical expression of functions, which may be the correspondence relationship given in the problem. Let's move on to the next question. The graph of the function r equal to fp is shown in the figure, and the local range of the function r equals fp is represented by an interval. How can we read the locality and value range of a function through its graph? We only need to project the graph of the function onto the horizontal axis, and then the set of values corresponding to it is the locality of the function. We project the image onto the vertical axis, and the set of corresponding values is the range of the function. This image, its projection on the horizontal axis corresponds to a closed interval of -5 to 0. This image is projected onto the horizontal axis, and its corresponding values are in the range of 2 to 6. But please note that 2 can be obtained, so it is a closed interval, while 6 cannot be obtained, so it is an open interval. So, if we project the image onto the vertical axis, the value corresponding to the projection of this image with the vertical axis is a closed range of 2 to 5, and this image is projected onto the vertical axis. The corresponding values are from 0 to positive infinity, so the range of values for the entire function should be the left closed and right open interval from 0 to positive infinity. We know that if we have a graph of a function, we can use it to assist us in reading out the localization and value range of the function. Let's take example 2. After traveling 10 kilometers, a high-speed train begins to run at a constant speed of 250 kilometers per hour. The first question is the collection of distances traveled by this high-speed train at a constant speed for 1 hour, 1.5 hours, and 3 hours. The collection of the distance traveled by this high-speed train when traveling at a constant speed for 1 to 3 hours. This problem is a practical problem in our daily life. Can you abstract it into a mathematical problem? What should be the corresponding relationship between the distance s traveled by high-speed rail and the time t? According to the question, we can obtain that s is equal to 250t plus 10. So in the first question, the range of values for t is actually the locality of my function. As we know from the first question, t can be equal to 1, 1.5, or 3. By substituting t into the analytical expression of the function, we can obtain the set of driving distances. The set consisting of 260, 385, and 760. In the second question, we know the range of t, greater than or equal to 1 and less than or equal to 3. So, because x equals 250t plus 10 is a linear function that we learned in junior high school. When the coefficient of t is positive, it represents an upward straight line, so we only need to input t equals 1 and t equals 3 into the function's analytical formula to obtain it. The set s corresponding to the distance s is greater than or equal to 260 and less than or equal to 760. From this question, we know that although the analytical expressions of functions are the same, their corresponding ranges of values are also different due to the second question. We know the range of t, greater than or equal to 1 and less than or equal to 3. So, because x equals 250t plus 10 is a linear function that we learned in junior high school. When the coefficient of t is positive, it represents an upward straight line, so we only need to input t equals 1 and t equals 3 into the function's analytical formula to obtain it. The set s corresponding to the distance s is greater than or equal to 260 and less than or equal to 760 is different definitions. Therefore, when studying a function, we must pay attention to its locality. So is there a function that has different locality, the same analytical expression, but the same range of values? Let's first look at example 3 with this question in mind. Find the function fx equal to x squared minus x plus 3. In the range of the following conditions, firstly, x belongs to R. Secondly, x belongs to the closed interval of 2 to 4. Thirdly, x belongs to the closed range of -1 to 4. In example 1, we know that if we can know the graph of a function, we can use the graph to assist us in reading out the value range of the function. For this function, x squared minus x3 is a quadratic function that we studied in junior high school, so we can first draw the graph of the quadratic function and find the range of its values under different conditions. This quadratic function opens upwards. The intersection points with the y-axis are 0 and 3. The axis of symmetry is x equal to 1. Estimate that the square of discriminant b minus 4ac equals 4 minus 12, which is less than 0, so the quadratic function graph has no intersection with the x-axis. We draw a graph of a quadratic function and then look at it to find the value range 1 of the function under different local conditions. If x belongs to R, we know that the quadratic function takes its minimum value at the symmetry axis. We only need to substitute 1 into the analytical formula of the quadratic function, where 1 minus 2 plus 3 equals 2. There is no maximum value when x belongs to the closed interval 2 to 4. At this point, it corresponds to the image. The minimum value is taken at 2, and the maximum value is taken at x equals 4. We only need to input x equal to 2 into the analytical formula, which yields 4 minus 4 plus 3 equals 3. Substituting 4 into 16 minus 8 plus 3 equals 11. So under the second condition, my range is 3 to 11. We will mark x as -1 to 4 in the image. At this point, we find that when x equals 1, we take the minimum value of the quadratic function, which is the 2 we just calculated. Substitute 4 into the function to obtain the maximum value of 11. Thus, we obtain the range of values for the quadratic function under each condition. The first y belongs to the left closed and right open interval from 2 to positive infinity. The second one is that y belongs to the closed range of 3 to 11. Thirdly, y belongs to the closed range of 2 to 11. In the process of handling this problem, have you noticed that for the second problem, we can directly substitute the endpoint values into the range of the function, while for the third problem, we cannot substitute the endpoint values of the independent variables into the range of the function? What is the reason for this? We know from the image just now, when the axis of symmetry is not within the given interval, we can bring the endpoint values into the direct range of values. If the axis of symmetry is within the given interval, then one pair of values must be taken at the axis of symmetry, and the other pair of values must be taken at a point far away from the axis of symmetry. If we generalize this issue, how can you summarize the quadratic function f(x) as x squared plus bx plus c, where x belongs to the range of b interval min? Through the special case just now, we can summarize the following steps to find the range of values of a quadratic function in a closed interval. Judge the relationship between symmetry axis x equal to b of negative 2a and interval m, n. If b of negative 2a of the symmetry axis does not belong to the given interval mn, then the endpoint of the value range is taken at fm, fn. If b of negative 2a belongs to a given interval m, n, then one endpoint of the value range must be taken at b of negative 2a of f, and the other endpoint must be taken at the endpoint far from the axis. Let's look at example 4 below. For the function we know, we can help us find the function range with the help of graphics.so. For this function, fx is equal to x squared minus the absolute value of 2x minus 1. Have we studied its image? Obviously, we haven't drawn the image of this function, but after you see this function, do you feel familiar? If there is no absolute value here, these are the three quadratic functions we just studied. Therefore, if we can remove the absolute value, we can convert the unknown function into the cognitive number for solution. How can we remove the absolute value? According to the meaning of absolute value, if the substitution formula in the absolute value is greater than or equal to 0, we should take it as itself when we remove the absolute value. If the substitution in absolute is less than 0, we should take its opposite number after removing the absolute value. So according to this absolute value property, we can convert this function. When x is greater than or equal to 1 second, fx is equal to x squared minus 2x plus 1. When x is less than 1 second, fx analytic expression is x squared plus 2x minus 1. In this way, we transform an unknown function into a function we know. When the first function becomes a familiar quadratic function, we can use the conclusion we just got to find the range of quadratic function. The symmetric axis x is equal to 1, and x is greater than or equal to 1 second, so the minimum value of this quadratic function should be taken at x1. We take 1 in, 1 minus 2 plus 1 equals 0. So the value range of the first function is y greater than or equal to o. For the second segment of quadratic function, its axis of symmetry is x equal to minus 1, and x is less than 1 second. So we can substitute negative 1 into the analytic expression of the function to get negative 2, so that the value range of the second segment of the function is y greater than or equal to negative 2. Therefore, the value range of the entire function should be y greater than or equal to negative 2. For a function we don't know, we transform it into a function we know to solve it by equivalent transformation, which is a common method for us to study function problems in high school. Let's look at example 5. The following is a table showing the results of several math tests and the average score of the class of 3 students in class 1 of a high school in the first year of high school. This table shows a correspondence relationship, which is actually a functional relationship. So who do we take as independent variable and who is more valuable as dependent variable? Obviously, we take the test number as the independent variable and the math scores of each student as the dependent variable, which is more valuable for research. Please analyze the math learning of these 3 students in the first year of senior high school. From the table, we clearly know the scores of each student in each exam, but on the whole, it is not easy for us to see the change trend of the scores in the table. Is there any other way to express this functional relationship? Is it convenient to use the analytic method? Obviously, if we use the analytic expression, we will find that there is no corresponding rule between each student's math score and the test number, so it is not convenient to use the analytic expression to express this function. Then we can also use the image method to express this correspondence. We regard the score y as a function of the test number x and use the image method to show that the function y is equal to fx, as shown in the figure. Let's use dots to express the scores of student A, student B, and student C. From the graphic point of view, student A's performance is always above the average, and his performance is very excellent. According to statistics, student A has outstanding learning ability and good learning habits. In high school learning, he can be good at summarizing methods and rules, and quickly enter the state. Look at student B. His score is sometimes above the average, sometimes below the average, and fluctuates greatly. It shows that student B has a certain learning ability, but his will quality is not enough, and he is not firm enough, so his grades are sometimes high or low. Look at student C again. Although the first exam is far from the average score of the class, but he has a strong will and good learning attitude. Through his own efforts, his achievements gradually improved. Let's summarize what we learned in this lesson. The definition domain of a function is the premise of studying the value domain of a function, and the value domain of a function cannot be studied without the definition domain of a function. We know that functions have different domains. If the analytic expression is the same, its value range may also be different. 2. It is necessary to master some methods for solving the value range of simple elementary functions, such as the primary function, quadratic function, and inverse proportional function that we have learned. For these functions, we can draw the function image first and help us find the value range of the function with the help of the image. 3. If we encounter some unknown functions, we will see whether we can use the method of equivalent transformation to transform them into the functions we know, and then use the combination of numbers and shapes to help us solve the range problem. 4. A reasonable choice of function representation is conducive to the study of function properties.